Okay, so for this lesson, we're going to take a look at prime factors and how they relate to prime and composite numbers. So when we're talking about factors, we're talking about the whole numbers that 6 is divisible by, or 12 is divisible by, or 24 is divisible by. All of the whole numbers that you can divide 6 by exactly are 1, 2, 3, and 6, which means that we refer to these as the factors of the whole number of 6. If I'm stating the factors of 15, I'm thinking, what are all the numbers I can divide 15 by, whole numbers, so that divides out evenly? Well, any number is always divisible by 1 and itself. But 15 is also divisible by 3 times 5. If I'm looking at 24, 24 is divisible by 1 in itself. It's divisible by 2 and 12. It's divisible by 3 and 8. And it's divisible by 4 and 6. If I'm determining the number of factors of any given number, well, if I was looking at 15, I can see I have 1, 2, 3, 4 different numbers. If I was looking at 24, I actually have 1, 2, 3, 4, 5, 6, 7, 8 different whole numbers I can divide it by. So when I'm looking at 3, 3 is only divisible by 1 and 3, so I have 2 possibilities. For 10, I can divide it by 1, 2, 5, and 10, so it has 4 different whole numbers I can divide it by. The number 1 can only be divided by 1. 7 is going to be 1 and 7, so there's 2 possibilities there. And 18 is divisible by 1, 3, 6, 18, 2, and 9. I have 6 possibilities here. So when we're distinguishing between prime and composite numbers, a prime number is one that has exactly 2 factors: the number 1 and the number itself. For example, 3 and 7. If we're talking about composite numbers, those are a number which has more than 2 factors. For example, when we took a look at the last case, we had 10 was divisible by 4 numbers, 18 was divisible by 6 numbers. Those are examples of composite numbers. The number 1 is unique because it only has 1 factor, so it's actually not prime and it's not composite. It's its own category. And the number 0 is considered to have no factors. So if I'm thinking of the first 10 prime numbers, then it's all the numbers that are divisible by only 1 in itself. Well, I have 2, 3, 5. Next would be 7, then 11, then 13, then 17, then 19, then 23, and then we go up to 29. So, if I am classifying numbers as whole numbers or as prime or composite numbers, I'm just seeing, is there any other number that I can divide it by other than 1 and itself? So for 46, it's an even number. Any even other than 2 will always be composite because it's always divisible by 2. For 37, I could go through all the numbers from 1 to 37, try and divide them, and the only ones that work are 1 and 37, so this is prime. For 39, it's actually also divisible by 3 and 13, so this is composite. And 101 and 103 are actually both prime. When I'm talking about prime factors specifically, prime factors are whole number factors that are prime. So even though 6 is divisible by 1, 2, 3, and 6, the only two factors that are also prime numbers are just 2 and 3. So if I stated all of the factors of 12, 12 is divisible by 1, 2, 3, 4, 6, and 12. It has 6 different factors. But if I'm listing just the factors that are prime, the only two prime number factors here are just 2 and 3. Well, if I'm expressing 12 as a product of prime factors, I'm saying what combinations of 2 and 3 would I have to multiply together to make 12? And I see that 12 is the same as if I took 2 times 2 times 3. We'd refer to this as the prime factorization, which means that we're taking a number and stating it as a multiplication just of prime factors. So if I'm trying to find the prime factorization, there's a couple of different methods we can use. We could use a division table where I'm just vertically listing the numbers, dividing out the smallest prime number until I can't do it anymore, and then dividing by the next prime number until I get 1. I can do a factoring tree where I'm going to take the number and split it up like branches on a tree until my base level only has prime numbers. And I'm going to state that it's going to be, if it's a division table, all of the prime numbers down the side multiplied by each other, or if it's a tree diagram, all of the numbers at the bottom branch or at the end of the branches that are prime numbers. So I can see either way I look at it, I have 4 2's and a 3, so I can write it as the expanded version, like this, or I can group together all of the same prime numbers, so if there's 4 2's, it's the same as 2 to the power 4, and get the exponent version. If I'm dividing down the number 2,772, and it wants me to, in this case, use a division table, I'm going to take 2,772, and I'm going to say, what's the smallest prime number I can divide that by? Well, I can divide this number by 2. And I'm left with 1,386. This is still divisible by 2. And I get 693. This isn't divisible by 2 anymore, but it is divisible by 3. And I'm left with 231. I can divide that number by 3. And I'm left with 77. That's not divisible by 3, or the next prime number 5, but it is divisible by 7. And I'm left with 11, which is a prime number that's only divisible by 11, and 1. So I'm going to state that 2,772 is the same as 2 times 2 times 3 times 3 times 7 times 11. I could also say that 2,772 is equal to 2 to the power of 2 times 3 to the power of 2 times 7 times 11. If I looked at the number 33,250, then I'm going to do a very similar process. First, I'm going to take that 33,250 and I'm going to divide it by 2 because I can see that it is an even number. And I get 2 and 16,625. I can see that this ends in 5, so I'm going to divide out 5 from here and get 3,325. Divide that by 5 again. And I get 665. I can divide that by 5. And I'm going to get 133. That's not divisible by 5, but I can divide that by 7. And I get 7 and 19. Now that I can see that it's all prime numbers on the bottom, I can state that 33,250 is equal to 2 times 5 times 5 times 5 times 7 times 19, or 2 times 5 to the power of 3 times 7 times 19. And there's the prime factorization. Go ahead and try some practice.